Hello, friend. Come sit with me for a while. Some nights the world feels wider than it should. Stars breathe slower. Time folds in silence. Maybe that's just the mind listening to itself. But there's one star we forget to see, the one that finds us every morning, that paints our ceiling gold, that warms the edge of our coffee cup. We call it the sun. We think we know it. But do we? Every day 93 million miles away, something impossibly old is burning. Not wood, not oil, not anything that rests on Earth. It burns hydrogen into helium, turning mass into light that takes 8 minutes to reach your skin. By the time you feel its warmth, the moment that made it has already passed. You've never seen the sun. Not really. You've seen its glow, its reflection, its echo. But the star itself, that's a thing too bright to witness, too vast to hold in thought. Tonight, we're going to drift closer. Before we begin, if you find comfort in these quiet journeys, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories told softly, and ring the little bell, not for noise, but so the next quiet night can find you again. Thank you. Now, let's drift. The sun is not a lamp. It's not a flame. It's a sphere of plasma, 109 times wider than Earth, held together by its own gravity. Scientists estimate it contains 99.86% of all the mass in our solar system. Everything else, the planets, the moons, the asteroids, the comets, even us, we're just the leftover crumbs. And yet, we rarely think about it. We wake, we see light, we assume it will return tomorrow. But that assumption rests on something fragile, a star that has been burning for 4.6 billion years and will burn for 5 billion more. We live in the brief, narrow window when it's neither too young nor too old, when it's just right. Some call that luck. Others call it the anthropic principle, the idea that we exist to observe the universe precisely because the conditions allow us to. If the sun were different, we wouldn't be here to wonder about it. But it is what it is, and so are we. The ancient Egyptians called it Ra. The Greeks called it Helios. The Aztecs called it Tonatiuh, and fed it blood to keep it alive. They believed the sun could die. They weren't wrong. It will. Just not in the way they imagined. For most of human history, we thought the sun was fire, literal fire, like the kind that burns in a hearth. Aristotle believed it was made of ether, a perfect, unchanging substance. Galileo in 1610 looked through his telescope and saw dark spots moving across its face. He realized the sun was not perfect. It had blemishes. It changed. That was heresy. The church did not like the idea of an imperfect heaven. But Galileo kept looking. And the more he looked, the less the sun seemed like a god. We see the sun as a constant. It rises, it sets, it returns. But scientists suggest it's anything but constant. It pulses, it breathes, it storms. Its surface roils with convection. Cells the size of Texas, each one a churning river of superheated gas. Plasma rises, cools, falls again and again in a rhythm that never stops. The light we see comes from a layer called the photosphere, the sphere of light. It's only about 300 miles thick, thinner than the distance between New York and Washington, D.C. Below it, the sun is opaque. Above it, transparent. The photosphere is the edge where the star decides to let its light escape. And that light, it's old. A photon born in the sun's core doesn't travel in a straight line. It bounces, it scatters. It careens off atoms again and again in a random walk that can take 100,000 years. By the time it reaches the surface and flies free, it's been wandering in the dark for longer than human civilization has existed. You are not seeing the sun as it is now. You are seeing the memory of what it was 100 millennia ago, finally set free. The sun's surface temperature is about 500 degrees Celsius, hot enough to melt tungsten, hot enough to vaporize bone. But here's the strange part. The atmosphere above it, the corona, is hotter, much hotter, over 1 million degrees. Scientists call this The coronal heating problem. Research shows that something magnetic fields, plasma waves, tiny explosions called nanoflares, must be pumping energy into the corona, but no one knows exactly how. The sun is hiding something from us even now. We've sent probes, we've built models, we've watched for decades, and still the sun keeps a secret. If you could stand on the sun, of course you can, but imagine you would weigh 28 times what you weigh on Earth. Gravity there is brutal. It crushes atoms together so tightly that hydrogen nuclei fuse into helium, releasing energy in the process. That's what we call nuclear fusion. That's the sun's heartbeat. Every second, the sun converts 600 million tons of hydrogen into helium. 4 million tons of that mass become pure energy radiated out into space. Einstein's equation, E = mc2, made flesh, or rather, made light. That energy travels outward. Some of it reaches us. Some of it drifts past Earth into the infinite dark, never to touch anything again. The sun doesn't choose where its light goes. It just gives. In the 19th century, before we understood, fusion scientists were baffled. Lord Kelvin calculated that if the sun were burning coal or wood, it would have exhausted itself in a few thousand years. But geologists had found rocks far older than that. The sun must have been shining for millions, maybe billions of years. How some proposed it was shrinking under its own gravity, releasing energy as it collapsed. But that only bought tens of millions of years. Not enough, not nearly enough. It wasn't until the 1930s, when Hans Bethe and others worked out the physics of nuclear fusion, that we finally understood. The sun wasn't burning. It was transforming. Matter into energy, mass into light, hydrogen into everything else. And in that moment, the sun stopped being magic. It became something better. It became understandable. But understanding doesn't make it less astonishing. Consider this: the sun produces more energy in 1 second than humanity has used in all of history. Every second. And it's been doing this for 4.6 billion years. It will keep doing it for 5 billion more, steady, patient, unfailing. We are warmed by the ash of hydrogen, the leftover light of atoms dying by the trillions. We are plants drinking in photons. We are creatures whose eyes evolved to see the narrow band of wavelengths the sun happens to emit most strongly. We are made by the sun and for it, even if it never meant to make us. There's a photograph taken by the Voyager 1 spacecraft in 1990 from 3.7 billion miles away. It's called the pale blue dot. Earth appears as a single pixel, a faint speck suspended in a sunbeam. Carl Sagan called it a mote of dust. But that speck is where everything we know exists. Every human who has ever lived, every story, every war, every love, every quiet night, all of it held in the embrace of a star that doesn't even know we're here. The sun doesn't shine for us. It shines because it must. Because gravity demands it. Because hydrogen under enough pressure has no choice but to become helium. And in that transformation, light happens. Life happens. We happen. You don't need to understand everything. You don't need to hold all of this in your mind at once. Just rest and let curiosity do the listening. The sun is closer than you think, not in distance and presence. It's in the oxygen you breathe, made by plants that drink its light. It's in the warmth of your skin. It's in the rhythm of your waking and sleeping, your body's ancient clock still tuned to a star. You are not separate from the sun. You are part of its story. And tonight, we'll follow that story deeper into the fire, into the heart, into the place where light first learned to be. Before there was light, there was only cloud, a vast cold nebula of hydrogen and helium drifting silently through the dark. No sun, no earth, no warmth. Just gas and dust scattered across a region larger than our solar system is now. It had been there for millions of years, perhaps billions. Quiet, patient, waiting for something to happen. And then something did. A shock wave. Maybe from a nearby supernova, a dying star's final scream. or perhaps the spiral arm of the Milky Way compressing gas as it passed. Scientists suggest that somewhere, somehow, a disturbance rippled through the cloud. And when it did, gravity woke up. The cloud began to collapse, not all at once, not everywhere. Just in one place, a pocket where the density was slightly higher, where gravity pulled just a little harder. And once it started, it couldn't stop. The more it collapsed, the stronger gravity became. The stronger gravity became, the faster it pulled. A feedback loop, a cosmic inevitability. This is how stars are born, not with fire, but with falling. At the center of the collapsing cloud, a knot began to form, denser, hotter, spinning faster as it shrank. The way a figure skater spins faster when they pull their arms in. This is called conservation of angular momentum, a law of physics that says rotation once started cannot be lost. Only concentrated, the knot grew. It pulled in more gas, more dust. It became a protostar, not yet a star, but something close, something trying. Research shows that protostars are messy, chaotic things. They flicker, they flare, they blast out jets of gas from their poles, carving tunnels through the cloud around them. They are stars in adolescence, awkward and unstable, not yet sure what they will become. For tens of thousands of years, the protostar that would become our sun was hidden, wrapped in a cocoon of dust, invisible to any eye that might have looked. But inside, something was building. Pressure, heat, density. The core was collapsing faster than the outer layers, crushing hydrogen atoms closer and closer together. 10,000 degrees, 100,000, 1,000,000, and still it wasn't enough. Nuclear fusion does not happen easily. Hydrogen nuclei are positively charged, and like charges repel. To make them fuse, you have to force them so close together that the strong nuclear force, the force that binds atomic nuclei, can take over. But to do that, you need extreme conditions. Scientists estimate that fusion ignites when the core reaches about 10 million degrees Celsius. At that temperature, hydrogen nuclei are moving so fast, colliding so violently that some of them overcome their repulsion and stick together. 4 hydrogen nuclei combine to form 1 helium nucleus. In the process, a tiny amount of mass disappears, converted into energy as Einstein predicted. That energy pushes outward against the crush of gravity. And for the first time, the star finds balance. Gravity pulls in. Fusion pushes out. Equal and opposite. Stable. The sun ignited. It took 50 million years from the first collapse to the first spark. 50 million years of waiting, of building of darkness. And then light. But the birth wasn't finished. The young sun was still surrounded by a disk of leftover gas and dust, the same material it had pulled from the nebula. This disk was thin, flat, spinning along with the star. Scientists call it a protoplanetary disk. And it's here in this disk that something astonishing happened. Dust grains no bigger than smoke particles began to stick together. Static electricity. Gentle collisions. Over thousands then, millions of years, they clumped into pebbles, then boulders, then planetesimals, bodies kilometers across. These collided too, sometimes merging, sometimes shattering. But over time, a few grew large enough that their own gravity pulled in everything nearby. Planets. Our sun didn't birth them consciously. It didn't plan them, but its gravity shaped the disk. Its heat melted ice close and leaving only rock and metal near the center: Mercury, Venus, Earth, Mars. Farther out where it was cold, ice survived. And ice is sticky. The giant planets, Jupiter, Saturn, Uranus, Neptune, grew fat on frozen water, methane, ammonia. By the time the sun was 10 million years old, the solar system had taken shape, a family born from collapse held together by gravity and light. There's a stage in a young star's life called the T Tauri phase, named after the first star of its kind we observed in the constellation Taurus. During this phase, the star is still gathering mass, still adjusting. It's violent. It throws tantrums. It blasts out powerful stellar winds that sweep the protoplanetary disk clean blowing away leftover gas that didn't form planets. Our sun went through this phase. For a few million years, it was unstable, unpredictable. The infant Earth, freshly formed and still molten, was battered by this wind. Stripped of any early atmosphere it might have had, scoured clean. But eventually the sun calmed, the fusion in its core steadied, the wind softened, and the planets now in stable orbits began their own journeys, cooling, solidifying, evolving. The sun had learned to shine, and in doing so, it had made a cradle for life. Here's something most people don't realize: the sun is still collapsing. Just very, very slowly. Every second, as hydrogen fuses into helium in the core contracts slightly. Helium nuclei are heavier than hydrogen and they sink. The core becomes denser, and as it does, it heats up just a little, enough to keep fusion going. Scientists estimate that over the past 4.6 billion years, the sun has grown about 30% brighter. Not because it's burning faster, but because its core is more compressed, more efficient. The early Earth was colder than it is now, not because of its atmosphere, but because the sun itself was dimmer. This slow brightening will continue. In 1 billion years, the sun will be bright enough that Earth's oceans will begin to evaporate. In 5 billion years, the core will run out of hydrogen entirely. And when that happens, the sun will change, drastically. But we'll come to that later. For now, think about this. Every atom in the sun's core was once part of a cold, dark cloud. Every photon warming your skin was born in the crush of fusion 100,000 years ago, and only just now escaped. The sun is not eternal, but it is ancient. It has been shining since before the Earth had solid ground, since before the moon existed, since before anything lived. And yet, it almost didn't happen. If the cloud had been just a little less dense, gravity wouldn't have been strong enough. The collapse would have stalled. The core would never have reached 10 million degrees. No fusion, no star. Just a cold, dark clump of gas drifting forever in silence. If it had been too dense, the collapse would have been too violent. The core would have overheated, blown itself apart, scattered back into space. No star, no planets, no us. The sun exists in a narrow window of possibility, and we exist because it does. When you look at the sun, carefully, never directly, you are looking at the result of 50 million years of collapse and 4.6 billion years of burning. You are seeing the light of a star that learned slowly, patiently how to be a star. It wasn't given instructions, it wasn't designed. It simply followed the laws of physics step by step until it became what it needed to be. And in that process, it made us possible. Some nights when the sky is clear, you can see other stars. Some are younger than the sun, still wrapped in their birth clouds, still figuring out how to shine. Some are older, redder, dying. Some exploded long ago, and their light is only just reaching us now, a memory traveling across time. Every one of them was born the same way: collapse, heat, fusion, light. Stars are not miracles, they are consequences. But that doesn't make them any less beautiful. The sun learned to shine because it had no choice. Because hydrogen under enough pressure becomes helium. Because gravity, once it starts pulling, does not stop. Because the universe has rules, and those rules followed far enough lead to light. We are the inheritors of that light. We are warmed by a fire that took 50 million years to ignite and will burn for 5 billion more. We are here in the brief bright window when the sun is neither too young nor too old, when it's just right. And that is not luck, that is physics, that is time. That is the quiet, patient work of a universe that makes stars not for us, but because it must. Rest in that thought. Let it settle gently like dust, falling through space, waiting to become something new. The sun learned to shine, and in doing so, it taught the universe how to see. Now, let's look deeper into the architecture of fire itself, into the layers where light is born and trapped and finally set free. Imagine peeling an onion layer by layer, each one different from the last. The sun is like that. Not uniform, not simple. It's a sphere built from zones, each with its own temperature, its own density, its own rhythm. Light doesn't leap from the core to your eyes in an instant. It travels through worlds, slow, trapped, transformed before it finally breaks free. Most people think the sun is just fire, but fire needs oxygen, needs fuel that burns away. The sun needs neither. It is plasma, a fourth state of matter beyond solid liquid gas. Atoms torn apart by heat electrons, ripped free nuclei floating in a sea of charge. It is matter that has forgotten how to be still. And within this plasma, there are layers, invisible borders, where the rules change, where the star becomes something else, something stranger. Let's descend. The core, that's where we begin. It's not large, only about a quarter of the sun's radius, maybe 150,000 kilometers across. But it contains more than half the sun's mass. Gravity has crushed everything here into a density 14 times that of lead. If you could hold a teaspoon of core material, of course you can't. It would weigh about 150 grams. Dense, but not impossibly so. Not yet a neutron star, just compressed. The temperature here is 15 million degrees Celsius. At this heat, hydrogen nuclei move so fast that when they collide, they fuse. 4 hydrogen nuclei become 1 helium nucleus. And in that transformation, 0.7% of the mass vanishes, converted into energy, into light, into the radiation's pressure that keeps the sun from collapsing further. Scientists estimate that every second, the core converts 600 million tons of hydrogen into helium. 4 million tons of that becomes pure energy. That energy is what we feel 93 million miles away as warmth on our skin. But the light doesn't escape immediately. It can't. The core is too dense. Photons, newborn and energetic, slam into electrons, into nuclei, scattering in random directions. They move a fraction of an inch, then hit something again. And again. And again. This is not a journey. It's a prison. Surrounding the core is the radiative zone, a layer that stretches from about 150,000 kilometers out to roughly 500,000 kilometers from the center. Here, the temperature drops. Still millions of degrees, but cooler than the core. Dense enough that photons still can't travel far without scattering. Research shows that a photon born in the core can take anywhere from 100,000 to 170,000 years to cross the radiative zone. Not because the distance is vast, but because the path is impossibly tangled. A random walk, a drunkard's stumble. Scientists call this a photon random walk. Each collision sends the photon in a new, unpredictable direction. By the time a photon finally leaves the radiative zone, it's been scattered so many times that it no longer remembers where it started. It's lost all sense of direction, and its energy has changed. High-energy gamma rays born in the core are gradually downgraded, absorbed, and re-emitted at lower frequencies. By the time they reach the next layer, they become X-rays, then ultraviolet, then visible light. The sun doesn't just make light, it softens it, grinds it down, makes it safe for eyes like ours. At about 70% of the sun's radius, something changes. The temperature drops below 2 million degrees Celsius, and at that threshold, the radiative zone ends. Heat can no longer travel efficiently by radiation alone. The plasma becomes opaque in a new way, not to light, but to convection. Welcome to the convective zone. Here heat moves like water boiling in a pot. Hot plasma rises from below, cools as it nears the surface, then sinks back down to be reheated. Giant convection cells, each one the size of Texas or larger churn and Royal. Scientists suggest these cells move at speeds of about 1 kilometer per second, slow by cosmic standards, but relentless. If you could see the sun's surface up close, you'd notice a pattern, a granulation like the texture of orange peel. Each granule is the top of a convection cell. The bright center is hot plasma rising. The dark edges are cooler plasma sinking back down. Each granule lasts about 8 to 20 minutes before it dissolves and reforms. The sun's surface is not calm. It seethes, it breathes, it never rests. And this convection, this churning of charged plasma does something else. It generates magnetic fields, twisting, tangling, emerging from the surface in loops and arcs. These fields are the reason the sun storms, the reason it flares, the reason it's dangerous. But we'll come to that. The top of the convective zone is what we call the photosphere, the sphere of light. It's a layer only about 500 kilometers thick thinner than the distance from Los Angeles to San Francisco. And it's here, finally, that photons escape. The temperature at the photosphere is about 500 degrees Celsius, hot enough to vaporize any metal we know. But compared to the core, it's cool enough that atoms can hold on to some of their electrons, cool enough that the plasma becomes translucent. Photons trapped for 100,000 years finally break free and race into space at the speed of light. This is the sun we see, the surface we measure, the edge where the star decides to show itself. But the sun doesn't end here. Just above the photosphere is a thin layer called the chromosphere, the sphere of color. It's only about 2,000 kilometers thick, and it glows a faint red, though you can only see it during a solar eclipse when the photosphere's brightness is blocked. The chromosphere is cooler than the photosphere, around 4,000 degrees Celsius near the bottom. But here's the strange part: as you go higher, it gets hotter. By the top, it's reached 20,000 degrees. This shouldn't happen. Heat doesn't flow from cold to hot, and yet it does. Scientists call this the temperature inversion problem. Something is pumping energy into the chromosphere from below, likely magnetic fields twisting and snapping, releasing energy in bursts. But the exact mechanism is still debated. The sun is full of mysteries. Some we've solved, some we're still chasing. Above the chromosphere is the transition region, a razor-thin layer where the temperature skyrockets. In just a few hundred kilometers, it jumps from 20,000 degrees to over 1,000,000. And then beyond that, the corona. The corona is the sun's outer atmosphere. It's vast, extending millions of kilometers into space far beyond the planets. And it's hot. Impossibly hot. 1 to 3 million degrees Celsius, sometimes more during solar storms. This is the coronal heating problem, one of the great unsolved puzzles in solar physics. The surface is 5,500 degrees. The corona is 200 times hotter. How energy doesn't flow uphill like that? Not on its own. Research suggests magnetic fields are the answer. The sun's magnetic field lines twist and tangle as the plasma below churns. When they reconnect, snapping like overstretched rubber bands, they release energy in violent bursts. Plasma is flung outward, waves ripple through the corona. Heat is deposited somehow in ways we don't fully understand. NASA's Parker Solar Probe, launched in 2018, is trying to solve this. It's flying closer to the sun than any spacecraft ever has, diving through the corona itself, measuring the temperature, the magnetic fields, the plasma flows. And slowly, piece by piece, we're learning. But the sun doesn't give up its secrets easily. Here's something to consider. The sun has no solid surface, no ground to stand on. The layers we've described, core, radiative zone, convective zone, photosphere, chromosphere, corona, they blend into each other. There are no hard borders, just gradients, just transitions. If you tried to descend into the sun, you wouldn't hit a wall. You'd just feel the plasma grow denser, hotter, brighter, until the pressure crushed you, and the heat vaporized you, and the radiation tore your atoms apart. You'd become part of the sun, indistinguishable from it. The sun is not a place, it's a process. A continuous transformation of matter and energy from the core outward forever. And yet we measure it, we map it, we name its parts as if they were organs in a body. In a way they are. The core is the heart, the radiative zone, the circulatory system, the convective zone, the lungs, the photosphere, the skin. The corona, the breath. Scientists have studied the sun for centuries, and we know more about it than any other star. But even now, it surprises us. Even now, it shows us things we didn't predict. In 2012, the Solar Dynamics Observatory captured footage of a solar prominence, a massive loop of plasma held aloft by magnetic fields. It was larger than Jupiter. It hung there for hours, arcing hundreds of thousands of kilometers above the surface, glowing faintly in ultraviolet light. And then slowly it collapsed back down, raining plasma onto the photosphere. It was beautiful and terrifying. A reminder that the sun is not tame. It is vast. It is powerful. And we live in its shadow, hoping it stays calm. Have you ever wondered why the sun looks yellow to us, even though the photosphere emits light across the entire visible spectrum? Red, orange, yellow, green, blue, violet. It's because of Earth's atmosphere. Blue light scatters more than red light, so the sky looks blue and the sun looks slightly yellow. In space, astronauts see the sun as white, pure, unfiltered starlight. Our perception of the sun is shaped by where we stand, by the air we breathe, by the eyes we evolved. We see the sun not as it is, but as it appears through layers of atmosphere, layers of biology, layers of interpretation. And still we try to see deeper, to peel back those layers, to understand the anatomy of fire. The sun is not one thing. It's a symphony of zones, each playing its own note. The core hums with fusion. The radiative zone glows with trapped light. The convective zone churns with motion. The photosphere radiates. The chromosphere flickers. The corona storms. Together, they make a star. Together, they make light. Together, they make us possible. And beneath all of it, beneath the heat and the light and the complexity, is something simple. Hydrogen, helium, gravity, time. The raw ingredients of existence following the only path they can. From chaos order, from collapse light, from fire life. But fire left unchecked is wild, and the sun's surface is not smooth. It's scarred, marked by dark spots that come and go, that shift and swirl, that tell stories of the magnetic storms raging below. Some stars wear their age on their surface, dark patches, temporary blemishes, marks that appear, linger, then fade. The sun has them too. We call them sunspots. And for centuries we thought they were flaws, imperfections in an otherwise perfect heaven. But they're not flaws. They're words. The sun speaking in a language we're only now learning to read. Every sunspot is a story. A knot of magnetic field bursting through the photosphere, cooling the plasma, darkening the surface. They come and go in cycles. They cluster and scatter. They tell us when the sun is restless and when it's calm. And if you know how to listen, they tell us something else. The sun has moods. The sun has rhythms. The sun remembers. In 1610, Galileo Galilei pointed his telescope at the sun, a dangerous thing to do, and he damaged his eyes doing it. But what he saw changed everything. Dark spots, moving across the sun's face, slowly day by day tracking from east to west. They weren't on the lens. They weren't clouds. They were on the sun itself. This was heresy. Aristotle had taught that the heavens were perfect, unchanging, eternal. The church had embraced this idea. The sun, being a heavenly body, should have been flawless. But here was Galileo showing that the sun had blemishes, that it changed, that it was in some way imperfect. The church did not respond kindly, but Galileo kept looking, and so did others. Scientists suggest that sunspots had been observed before Galileo. Chinese astronomers recorded them as early as 800 BCE, visible to the naked eye during dusty sunsets. But Galileo was the first in Europe to study them systematically, to track their movement, to realize they were features of the sun itself, not objects passing in front of it. He noticed something else too. The spots move faster near the sun's equator than near its poles. The sun, he realized, was not solid. It rotated differentially faster at the middle, slower at the edges, like a fluid. The sun was not a sphere of ether. It was plasma. It was alive. Sunspots are cooler than the surrounding photosphere, about 3,800 degrees Celsius compared to the usual 5,500. That might not sound like much, but it's enough to make them appear dark by contrast, like shadows cast by magnetism itself. And that's exactly what they are. Research shows that sunspots form where magnetic field lines pierce the surface. The sun's interior is a churning sea of plasma, and plasma is conductive. As it moves, it drags magnetic fields with it, twisting them, tangling them, amplifying them. Eventually, these fields grow so strong that they break through the photosphere like roots bursting through pavement. Where a magnetic field emerges, it suppresses convection. Hot plasma can't rise as easily. The surface cools. A sunspot forms. Most sunspots come in pairs, one where the magnetic field exits the sun, one where it loops back in. North and south poles, connected beneath the surface by an invisible arc of magnetism. Scientists call these active regions, and they can be vast. The largest sunspots ever recorded were larger than Jupiter. If you could see magnetic fields the way you see light, the sun would look like a tangled mess of glowing threads constantly shifting, constantly reorganizing. Sunspots are just the places where those threads puncture the surface. Sunspots don't last forever. Small ones fade in days. Large ones can persist for weeks, even months. The longest-lived sunspot on record lasted for about 8 months in 1943, rotating with the sun, slowly shrinking until finally it vanished. But while they're there, they're dangerous. Sunspots are the breeding grounds for solar flares and coronal mass ejections, violent eruptions that can send radiation and plasma hurtling toward Earth. The more sunspots there are, the more active the sun becomes. The more likely it is to storm, and the number of sunspots changes, predictably, in cycles. In the mid-1800s, a German astronomer named Heinrich Schwabe spent 17 years counting sunspots. Every clear day he observed the sun, sketched what he saw, recorded the number of spots. It was tedious work, but slowly a pattern emerged. The number of sunspots rose and fell over roughly 11 years. Some years the sun was covered in spots, dozens, sometimes hundreds. Other years it was nearly blank. And then the cycle would repeat. Scientists now call this the solar cycle. We're currently in solar cycle 25, which began in 2019. The last solar maximum, the peak of sunspot activity, occurred around 2014. The next one is expected around 2025, but the cycle isn't perfectly regular. Some maxima are stronger than others. Some minima are deeper. The sun is not a clock. It's more like a heartbeat, steady, but with variation. With personality. During solar minimum, the sun can go weeks without a single visible sunspot. The surface looks smooth, calm, almost peaceful. But this doesn't mean the sun is inactive. It just means the magnetic fields are hidden, tangled beneath the surface, waiting to rise again. During solar maximum, the sun is covered in spots. Active regions bloom and fade. Flares erupt. The corona grows brighter, more structured. The sun becomes unpredictable. Research shows that the solar cycle is driven by a process called the solar dynamo, the interaction between the sun's rotation and its convective motions, which generates and amplifies magnetic fields. Every 11 years, the sun's magnetic field flips. North becomes south. South becomes north. And as it does, the old sunspots fade and new ones appear, shifted in latitude, rotated in polarity. The sun is constantly reinventing itself. Every cycle, it starts over. But there have been times when the cycle failed. Between 1645 and 1715, a period known as the Maunder Minimum, sunspots almost disappeared. Astronomers across Europe observed the sun regularly, but they saw almost nothing. A few spots here and there, but far fewer than usual. The 11-year cycle seemed to stop. And during that time, something else happened. Europe grew colder. The Thames River in London froze over regularly. Glaciers in the Alps advanced. Winters were longer, harsher. Crops failed. Scientists call this the Little Ice Age, and while the causes are complex, volcanic eruptions, ocean circulation patterns, the timing matches the Maunder minimum too closely to be coincidence. Some researchers believe that when the sun is less active, it emits slightly less energy. Not much, maybe 0.1% less. But over decades, that's enough to cool the Earth, enough to matter. The Maunder minimum ended around 1715. Sunspots returned, the solar cycle resumed, and slowly the Earth warmed again. The sun doesn't just light our days, it shapes our climate. It governs the rhythms of the planet, and when it changes even slightly, we feel it. On September 1st, 1859, astronomer Richard Carrington was sketching sunspots in his private observatory in England. He was one of the most experienced solar observers of his time, and he had seen thousands of spots before. But that day, he saw something new. A sudden flash of white light. Bright, intense, erupting from a sunspot group. It lasted only 5 minutes, but it was unlike anything he'd ever witnessed. 17 hours later, the night sky over much of the Earth began to glow. Auroras, brilliant curtains of red, green, and purple light appeared as far south as the Caribbean. Telegraph systems across Europe and North America went haywire. Sparks flew from telegraph machines. Papers caught fire. Operators received electric shocks. Some lines continued to send messages even after their power sources were disconnected. Scientists now call this the Carrington event, the most powerful solar storm in recorded history. What Carrington saw was a solar flare, a massive burst of radiation from a sunspot. And what followed was a coronal mass ejection, a billion-ton cloud of plasma hurled toward Earth. When it hit, it compressed Earth's magnetosphere, inducing electrical currents in the ground. And in an age when the most advanced technology was the telegraph, that was enough to cause chaos. If a Carrington-level event happened today, the damage would be catastrophic. Satellites would fail, power grids would overload, GPS systems would go offline, communication networks would collapse. Scientists estimate the economic cost could reach trillions of dollars. And it could happen. Sunspots like the ones Carrington observed still form. The sun still storms. We're just better at watching now. Modern solar observatories like NASA's Solar Dynamics Observatory, launched in 2010, monitor the sun constantly. They track sunspots, measure magnetic fields, watch for flares. When a major eruption occurs, we get a warning, usually a few hours to a few days, depending on how fast the plasma is moving. That's not much time, but it's enough to shut down satellites, reroute power, prepare. It's enough to avoid the worst, but we can't stop the sun. We can't calm it. We can only watch and hope it stays gentle. Have you ever noticed that sunspots tend to appear in bands symmetrically placed north and south of the sun's equator? At the start of a solar cycle, they form at higher latitudes around 30 degrees north and south. As the cycle progresses, they drift toward the equator. By solar minimum, they're clustered near the equator, and then the cycle begins again, with new spots appearing at higher latitudes. Scientists call this Spurer's law, named after Gustav Spörer, who first documented the pattern in the 1860s. It's one of the clearest signs that the sun's magnetic field is organized, structured, following rules we're still working to understand fully. If you plotted sunspot latitudes over time, you'd see a pattern called the butterfly diagram, two wings mirrored across the equator, drifting inward as the cycle progresses. It looks almost intentional, almost designed, but it's not. It's just physics, magnetism and motion following the only path they can. Sunspots are not flaws. They're proof that the sun is dynamic, that it changes, that it breathes. Every spot is a scar left by a magnetic storm. Every scar is a memory, and when we count them, track them, study them, we're reading the sun's diary. We're learning its history. We're predicting its future. The sun has been making sunspots for as long as it's been shining. Long before humans looked up. Long before Galileo aimed his telescope skyward. long before anyone thought to ask why. And it will keep making them long after we're gone. The sun doesn't need an audience. It just does what it does, quietly, relentlessly, forever. But we're here now, and we're watching. And slowly we're learning to speak its language. And sometimes when the sun grows restless, when its magnetic fields twist and snap and surge, it does more than whisper. It shouts, it roars, it sends pieces of itself hurtling into the dark. There are moments when the sun forgets to be gentle, when magnetic fields twisted beyond tolerance snap, when plasma held aloft for days suddenly falls, when energy trapped beneath the surface finds a crack and erupts violent, brilliant, unstoppable. We call these events solar storms, flares, eruptions, explosions of light and matter flung into space at millions of miles per hour. Most of them miss us. Space is vast and Earth is small, but sometimes the sun aims true. And when it does, the consequences ripple across the planet, invisible but felt, in satellites, in power grids, in the sky itself. The sun is not always kind, and we live at its mercy. A solar flare is not fire, it's not combustion. It's the sudden release of magnetic energy that's been building for days, sometimes weeks, as the sun's magnetic field lines tangle and strain. Imagine stretching a rubber band. The more you stretch, the more energy it stores. Eventually it snaps. That snap releases the stored energy all at once. Solar flares work the same way. Magnetic field lines anchored in sunspots twist as the sun rotates. The twisting stores energy. And when the fields reconnect, when they snap back into a simpler configuration, that energy is released. Not as motion, but as light, as radiation. Scientists classify solar flares by their X-ray brightness. C-class flares are small, barely noticeable. M-class flares are medium enough to cause brief radio blackouts. X-class flares are the strongest, powerful enough to disrupt satellites, interfere with GPS, and flood Earth's upper atmosphere with radiation. The largest flare ever recorded occurred on November 4th, 2003. It was so intense it overloaded the sensors on the GOES satellite, the instruments that measure solar X-rays. Scientists estimate it was at least an X to 28, possibly as high as X45. For comparison, most X-class flares peak around X1 or X2. That flare lasted only 11 minutes. But in that time, it released more energy than 1 billion hydrogen bombs. And it wasn't even aimed at us. If it had been, the damage would have been catastrophic. When a solar flare erupts, the radiation reaches Earth in 8 minutes, the same time it takes sunlight to arrive. There's no warning, no time to prepare. The X-rays and ultraviolet light slam into the upper atmosphere, ionizing the air, disrupting radio signals, heating the thermosphere. High-frequency radio, the kind used by airplanes flying over polar regions, can go silent for hours. GPS signals scatter and degrade. Satellites in low Earth orbit experience increased drag as the atmosphere expands. But flares are only the first blow. Often they're followed by something worse: coronal mass ejections, CMEs. A CME is not radiation, it's matter. Billions of tons of plasma superheated magnetized gas hurled into space in a single explosive burst. Research shows that CMEs originate in the sun's corona, the outer atmosphere. When magnetic field lines above a sunspot group become too twisted, too unstable, they can suddenly release not just energy, but the plasma trapped within them. The field lines snap outward, carrying a bubble of plasma, with them accelerating it to speeds of 1,000 to 3,000 kilometers per second. If you could see a CME from space, it would look like a shock wave, a ripple expanding outward from the sun, carrying with it a glowing cloud of charged particles. Some CMEs are narrow-directed. Others are massive, expanding across a quarter of the sun's visible hemisphere. And if one of them is pointed at Earth, we have about 1 to 3 days before it arrives. That's how long it takes for plasma to cross 93 million miles. Slower than light, but faster than anything else the sun throws at us. When a CME reaches Earth, it doesn't hit the surface. It hits the magnetosphere, the invisible magnetic shield that surrounds our planet, generated by the motion of molten iron in Earth's core. The magnetosphere deflects most of the solar wind, the constant stream of particles flowing from the sun. But a CME is different. It's denser, faster, more energetic. When it arrives, it compresses the magnetosphere, squeezing it like a fist. On the side facing the sun, the magnetosphere is pushed inward sometimes as close as 25,000 kilometers above the surface, about twice the altitude of GPS satellites. On the night side, it stretches, forming a long tail that extends past the moon. And as the magnetosphere compresses, it generates electric currents. These currents flow along magnetic field lines, spiraling down toward the poles. And when they reach the upper atmosphere, something beautiful happens. Auroras. The aurora borealis, the northern lights, curtains of green, red, purple, and blue shimmering across the Arctic sky. They are caused by charged particles from the sun, electrons and protons, colliding with oxygen and nitrogen atoms in the thermosphere. The collisions excite the atoms, causing them to emit light. Oxygen glows green at lower altitudes, red at higher. Nitrogen glows blue and purple. Scientists suggest that auroras have been witnessed for thousands of years. Ancient Norse legends called them the Bifrost, the bridge between Earth and the realm of the gods. Inuit peoples believed they were the spirits of the dead dancing. Medieval Europeans thought they were omens of war. But they're not supernatural. They're plasma. They're magnetism. They're the sun touching the Earth in the only way it can. During a strong geomagnetic storm, auroras can be seen far from the poles. During the Carrington event in 1859, auroras were visible as far south as Cuba and Hawaii. People in the Rocky Mountains woke at midnight thinking it was dawn. The sky was that bright. Imagine that. A storm so powerful it turned night into day across half the planet. But auroras are the beautiful part, the part we celebrate, photograph, travel to see. There's another side, a side we don't see but feel in more dangerous ways. Geomagnetically induced currents, GICs. When the magnetosphere is disturbed, it induces electric currents in the ground. These currents flow through anything conductive: pipelines, railway tracks, and most critically, power lines. Power grids are designed to carry alternating current at specific frequencies. But GICs are direct current, slow and unpredictable. When they flow through transformers, the massive devices that step voltage up or down, they can overheat the transformer's core, saturating it, damaging it, sometimes destroying it. On March 13, 1989, a powerful CME struck Earth. Within 90 seconds, the entire province of Quebec, Canada lost power. 6 million people were plunged into darkness. Transformers failed. The grid collapsed. It took 9 hours to restore power. Some transformers were permanently damaged, and Quebec was lucky. The storm could have been worse. The damage could have spread. Scientists estimate that a Carrington-level event today could leave tens of millions without power for weeks, even months. Replacing damaged transformers takes time. They're custom-built, massive, expensive. There aren't stockpiles sitting in warehouses. If the grid goes down for that long, the consequences cascade. No refrigeration, no water pumps, no communication. Modern society in many ways runs on electricity, and a strong enough solar storm could take that away. Space is not empty, and it's not safe. Astronauts on the International Space Station are protected mostly by Earth's magnetosphere, but they're at the edge of it. During a major solar storm, radiation levels inside the ISS can spike. Astronauts are instructed to move to the most shielded areas to limit their exposure. Outside Earth's magnetosphere, the danger is greater. The moon has no magnetic field, no atmosphere. During a solar storm, the surface is bathed in radiation. Future lunar bases will need thick shielding underground habitats, warning systems. And for missions to Mars, the risk is even higher. The trip takes 6 to 9 months. If a major solar storm occurs en route, astronauts in a spacecraft with limited shielding could receive a lethal dose of radiation. There's no running, no hiding, just waiting, hoping the storm passes quickly. Scientists are working on solutions: faster spacecraft to shorten the journey, better shielding materials, storm shelters inside the ship, early warning systems that monitor the sun and predict eruptions. But the sun is unpredictable, and space is unforgiving. In October 2003, a series of powerful solar storms struck Earth in rapid succession. Scientists call it the Halloween storms. On October 28th, an X-17 class flare erupted, the second strongest on record at the time. Hours later, a massive CME followed. Then another flare, another CME. For 2 weeks, the sun raged. Satellites were damaged. The Mars Odyssey spacecraft had to be temporarily shut down to protect its instruments. Airlines rerouted flights away from polar regions to avoid radiation exposure for passengers and crew. Power grids in Sweden experienced disturbances. Auroras were seen as far south as Texas and Florida. And then, on November 4th, came the X-28 flare, the one that overloaded the sensors. The one that could have been an X-45. The sun was screaming, and we could only watch. Have you ever wondered what would happen if a massive CME hit during a solar maximum when the sun is already hyperactive and multiple active regions are flaring at once? In July 2012, it almost happened. A Carrington-level CME erupted from the sun, one of the fastest, most powerful ever observed. Scientists estimate it was moving at over 3,000 kilometers per second, carrying a magnetic field 4 times stronger than typical. But it missed. It erupted from a region on the far side of the sun, aimed away from Earth. If it had happened 1 week earlier when that region was facing us, it would have hit. NASA scientists later estimated that the economic cost of such an event could exceed $2 trillion, and recovery could take years. We dodged a bullet, a billion-ton bullet traveling at 1,000,000 miles per hour, and we didn't even know it was coming until it had already passed. Modern satellites watch the sun constantly. The Solar and Heliospheric Observatory SOHO has been monitoring the sun since 1995. The Solar Dynamics Observatory, launched in 2010, captures images in multiple wavelengths, tracking sunspots, flares, CMEs in real time. When a major eruption occurs, scientists analyze the data. They estimate the speed of the CME, its direction, its magnetic orientation. They calculate when it will arrive, how strong the geomagnetic storm will be, and they issue warnings. NOAA's Space Weather Prediction Center monitors this constantly. When a CME is Earth-directed, they alert power companies, satellite operators, airlines. There's time to prepare. Not much, but some. And yet we can't stop it. We can't shield the planet. We can only watch and brace and hope the sun shows mercy. The sun doesn't aim. It doesn't target. It simply erupts, and the plasma goes where physics takes it. Most CMEs fly harmlessly into space, never touching anything. A few hit other planets, Venus, Mars, Jupiter, and occasionally one finds Earth. Not because the sun is angry, not because we did something wrong, but because we orbit a star, and stars are violent. And sometimes violence finds us. But here's the paradox: we need that violence. The sun's magnetic activity, the storms, the flares, they're driven by the same dynamo that powers the solar cycle. And the solar cycle is part of what keeps the sun stable, predictable, long-lived. If the sun didn't storm, if its magnetic fields never twisted and snapped, something else would be wrong, something deeper. And we'd have bigger problems than broken satellites. The sun storms because it's alive, because it's dynamic, because it's doing what stars do. And we, small and fragile, watch from a safe distance, hoping it never looks directly at us. But the sun doesn't just throw plasma into the dark. It breathes constantly, endlessly, a wind that never stops flowing outward through the solar system and beyond. the sun hums. Not in a way you can hear, not with sound waves traveling through air, but deep within its plasma heart, the sun vibrates millions of frequencies overlapping, resonating, creating patterns that ripple across its surface like waves on an ocean. If you could listen, you'd hear a chord, not a single note, but a symphony, a harmony of motion, driven by convection, shaped by gravity, sustained for billions of years. We can't hear it, but we can see it. And in seeing, we've learned to read the sun's interior, to peer beneath the photosphere into layers. No light escapes into the places where fusion burns and plasma churns. The sun's heartbeat, slow, steady, infinite. And we've only just begun to understand what it's telling us. In the early 1960s, astronomer Robert Layton was studying the sun's surface using a telescope equipped with a Doppler spectrometer, an instrument that measures how fast something is moving toward or away from you based on shifts in the wavelength of light. He expected to see convection plasma rising and falling, driven by heat. And he did. But he also noticed something strange. The surface was oscillating, moving up and down in regular pulses with a period of about 5 minutes. Not chaotic, not random. Organized, rhythmic. At first, scientists thought it might be an artifact, an error in the instrument. But other observatories confirmed it. The sun's surface was ringing like a bell. Scientists now call these oscillations P modes, short for pressure modes. They're sound waves, acoustic waves trapped inside the sun, bouncing between the core and the surface, creating standing wave patterns that make the photosphere rise and fall. Imagine striking a bell. The sound doesn't just radiate outward, it also travels through the metal, reflecting off the surfaces, creating patterns of vibration. The bell rings because those waves interfere, constructively reinforcing certain frequencies while canceling others. The sun works the same way. Sound waves generated by the turbulent convection zone travel downward into the sun's interior. As they descend, the density increases, the speed of sound increases, and the waves refract, bending back toward the surface. They bounce, they return, they interfere, and the photosphere caught in this web of oscillations breathes. Research shows that the sun supports about 10 million different oscillation modes. Each mode has a specific frequency, a specific pattern of motion across the surface. Some modes involve the entire sun. Others are localized to certain latitudes. Some penetrate deep into the core. Others barely skim the surface. By measuring which modes are present and how strong they are, scientists can infer the sun's internal structure. The speed of sound depends on temperature and density. So, if you know how fast the sound waves are traveling, you can deduce what the interior is like. This field is called helioseismology, literally sunquake science. It's similar to how geologists use seismic waves from earthquakes to study Earth's interior. We can't see inside the planet, but we can watch how waves travel through it. And from that, we can build a map. The same is true for the sun. We can't see the core, but we can hear it. In the trembling of the surface and the 5-minute oscillations, we find echoes of the fusion furnace 700,000 kilometers below. The 5-minute oscillation, the most prominent P mode, is driven by sound waves with a wavelength of about 10,000 kilometers. These waves travel at roughly 100 kilometers per second, bouncing between the photosphere and a depth of about 200,000 kilometers. But there are faster modes and slower modes. Some take 3 minutes to complete a cycle, some take 8. Together they create a complex shifting pattern, like ripples on a pond but in 3 dimensions and sustained by a star. If you could watch the sun in time-lapse tracking the motion of each point on the surface, you'd see it covered in ripples, thousands of them, overlapping, interfering, creating regions that rise and fall in sync, and regions that move out of phase, canceling each other out. Scientists call this the power spectrum of the sun, a graph that shows which frequencies are present and how strong they are. And buried in that spectrum is information. The depth of the convection zone. the rotation rate of the core, the abundance of helium in the radiative zone. We've turned the sun into an instrument, and we're learning to read its music. One of the most surprising discoveries from helioseismology is that the sun's core rotates faster than its surface. At the equator, the photosphere completes one rotation every 25 days. Near the poles, it takes about 35 days. This is differential rotation, the same effect Galileo noticed when tracking sunspots. But scientists wondered, does the interior rotate the same way? Or is it more rigid, more uniform? Helioseismology gave the answer. The radiative zone below the convection zone rotates almost like a solid body, uniformly at about 27 days per rotation, regardless of latitude. But the convective zone above it rotates differentially faster, at the equator, slower at the poles, and at the boundary between the two, a thin layer called the tachocline. The rotation rate changes sharply. This is where the sun's magnetic field is thought to be generated, where the dynamo operates, where the 11-year solar cycle is born. The tachocline is only about 20,000 kilometers thick, less than 3% of the sun's radius. But it's one of the most important layers. Without it, there would be no sunspots, no flares, no coronal mass ejections, no solar cycle. The sun's heartbeat begins here. In the friction between two zones rotating at different speeds, magnetic fields are stretched, twisted, amplified, and eventually they rise. Helioseismology has also revealed something unexpected about the sun's age. For decades, scientists assumed the sun had been converting hydrogen into helium at a steady rate since it was born. But helioseismology allows us to measure the abundance of helium in the core. And the measurements suggest that the core contains about 34% helium by mass, less than some models predicted. This tells us something subtle but profound. The sun's fusion rate has not been perfectly constant. It's increased slightly over time as the core has contracted and heated. And that increase matches what we see in the solar brightness trend. The sun today is about 30% brighter than it was when it first ignited. The sun is aging, slowly, predictably, but not imperceptibly. And we can measure it not by watching it shine, but by listening to it vibrate. In the 1970s, a scientist named John Bacall was studying the nuclear reactions in the sun's core. He calculated how many neutrinos, ghostly, nearly massless particles produced by fusion, the sun should be emitting. Neutrinos barely interact with matter. They pass through the Earth as if it weren't there. But occasionally, very rarely, one collides with an atom. And if you build a detector large enough, you can catch a few. Bacall's calculations predicted that detectors on Earth should see a certain number of solar neutrinos. But when experiments were conducted, they detected only about a third of the expected amount. This was called the solar neutrino problem. Either the models of the sun's core were wrong, or something strange was happening to the neutrinos on their way to Earth. For decades, scientists debated. Some proposed that the sun's core was cooler than expected, producing fewer neutrinos. Others suggested the neutrinos were changing, transforming from one type to another, a process called neutrino oscillation. Helioseismology helped resolve the debate. By measuring the speed of sound in the core, scientists confirmed that the temperature was right. The core was exactly as hot as the models predicted. The problem wasn't the sun, it was the neutrinos. Later experiments confirmed neutrino oscillation. Neutrinos do change type, and that means they have mass, which was a surprise, a discovery that won the Nobel Prize in 2015. The sun's heartbeat helped solve a mystery about the fundamental nature of matter, not by producing particles, but by vibrating, by singing the structure of its core into the light. Have you ever stood on a bridge and felt it sway slightly under your feet? That sway is the bridge's natural frequency, the rate at which it wants to oscillate, determined by its size, its materials, its structure. The sun has natural frequencies too, millions of them. But unlike a bridge, the sun is not fixed in place. It's a ball of plasma held together by gravity, heated from within, stirred by convection. And that makes its oscillations far more complex. Some modes involve only the surface layers. Others reach deep into the radiative zone. Some are symmetric, affecting the entire sun equally. Others break that symmetry, creating patterns that spiral around the equator or cluster near the poles. Scientists have cataloged thousands of these modes, and each one tells a story about the depth of the convection zone, about the sharpness of the tachocline, about the stiffness of the core, about the presence of magnetic fields, which can shift the frequencies slightly, adding another layer of information. The sun is not opaque, not anymore. We have learned to see through it, not with light, but with sound, with vibration, with the patience to watch the surface tremble and decode what that trembling means. In 1995, the European Space Agency and NASA launched SOHO, the Solar and Heliospheric Observatory. One of its primary instruments was designed for helioseismology. It could measure the velocity of every point on the sun's visible surface, tracking the oscillations continuously without interruption. Before SOHO, helioseismology was limited by weather, by day-night cycles, by the fact that Earth-based observatories could only watch the sun part of the time. SOHO changed that. It orbits at a point called L1, a gravitationally stable location between Earth and the sun. From there, it has an unobstructed view, always. For nearly 30 years, SOHO has been watching the sun vibrate, and the data it's gathered has transformed our understanding of the sun's interior. We now know the thickness of the convection zone to within a few hundred kilometers. We know how fast the core rotates. We know where the magnetic dynamo operates. We've mapped the inside of a star, not by going there, not by digging, but by listening. Helioseismology has also revealed that the sun's oscillations are not perfectly stable. The frequencies shift slightly over the solar cycle. When sunspots are abundant, when the magnetic fields are strong, the oscillations change. Certain modes are suppressed, others are amplified. Scientists suggest this is because the magnetic fields alter the structure of the convection zone. They disrupt the flow of plasma. They add tension like strings on an instrument. And the sun responds by changing its tune. If you track the sun's oscillation frequencies over decades, you'd see them rise and fall in sync with the 11-year cycle. The sun's heartbeat speeds up and slows down, not randomly, but in rhythm with its magnetic breath. It's as if the sun is singing about its moods, and we've learned to recognize the melodies. The sun is not silent. It never has been. It's been humming for 4.6 billion years, vibrating in patterns we're only now beginning to understand. Every wave that ripples across the photosphere carries information. Every oscillation is an echo of the interior. Every 5-minute pulse is a message from a place we'll never see. And we're listening, not with ears, but with spectrometers, with satellites, with mathematics, with patience. The sun's heartbeat is steady. It doesn't falter. It doesn't skip. It just beats endlessly in a rhythm set by gravity and heat and the laws of physics. And in that rhythm, we find answers to how stars age, to how magnetic fields are born, to whether our models of stellar interiors are correct. The sun has become a laboratory, a test case for everything we think we know about stars, and so far it's confirming most of our theories. The speed of sound matches the predictions. The rotation profile makes sense. The helium abundance is consistent with the age. But there are still mysteries, still frequencies that don't quite fit, still patterns we don't fully understand. The sun is not done teaching us, and we're not done listening. But the sun does more than hum. It exhales a constant stream of particles flowing outward, filling the solar system with a wind that never stops, a breath that reaches farther than any light. The sun is always exhaling, not air, not gas in the way we understand it, but a stream of charged particles, electrons, protons, ions flowing outward from the corona at hundreds of kilometers per second, filling the space between the planets, pushing against the edges of the solar system, never stopping, never resting. We call it the solar wind. But it's not gentle, it's not a breeze, It's a river of plasma, invisible but relentless, carrying with it the sun's magnetic field, shaping the environment of every world it touches. Earth sits inside this wind. Always has, always will, and without a shield, we'd be swept away. The sun breathes out, and the solar system listens. For most of human history, we thought space was empty, a void, nothingness between the stars and planets. But in the 1950s, a physicist named Eugene Parker proposed something radical. He suggested that the sun's corona, the outer atmosphere millions of degrees hot, was so energetic that it couldn't stay bound to the sun. The gas, he argued, must be continuously escaping, flowing outward into space, not in bursts, not occasionally, always. He called it the solar wind, and almost no one believed him. The idea seemed absurd. How could the sun be losing mass constantly and still exist? Wouldn't it evaporate? Wouldn't it run out? Parker did the math. He showed that the corona's temperature was high enough to overcome the sun's gravity. The particles at the top of the atmosphere were moving so fast that they could escape, and once they started moving outward, there was nothing to stop them. The sun, Parker argued, wasn't just shining, it was bleeding, slowly, continuously, into the dark. In 1962, NASA launched Mariner 2, a spacecraft bound for Venus. It carried instruments designed to measure the space environment between Earth and Venus, and what it found confirmed Parker's prediction. There was a wind, a steady stream of particles flowing from the sun at about 400 kilometers per second. Not turbulent, not chaotic. Smooth, almost laminar like a river. Scientists estimate that the sun loses about 1 million tons of matter every second through the solar wind. That sounds like a lot. But the sun is massive. At this rate, it would take 150 billion years to lose just 0.01% of its mass. The sun isn't evaporating, it's just breathing. And the breath is thin, barely a whisper in the vastness of space. But that whisper shapes everything. The solar wind originates in the corona. At the base of the corona, near the photosphere, the plasma is still dense enough to be held by gravity. But higher up, the density drops. The temperature stays high, over 1 million degrees. And at those temperatures, particles move fast. Hydrogen ions, protons at the top of the corona, are moving at hundreds of kilometers per second, fast enough to escape the sun's gravitational pull. And once they do, they accelerate. The pressure gradient pushes them outward faster and faster until they reach supersonic speeds. Research shows that the solar wind isn't uniform. There are two types, slow and fast. The slow solar wind flows at about 400 kilometers per second. It originates from the equatorial regions where the sun's magnetic field is more complex, more tangled. Plasma gets trapped in loops, heated, released gradually. The fast solar wind flows at 700 to 800 kilometers per second. It comes from regions called coronal holes, areas where the magnetic field lines are open, not looped back to the surface. Plasma can escape freely, accelerating quickly, streaming into space unimpeded. If you could see the solar wind, it wouldn't look uniform. It would look like streams, fast and slow, interleaving, spiraling outward as the sun rotates. And threaded through it, invisible but powerful, is the sun's magnetic field. The sun's magnetic field doesn't stay behind when the plasma flows outward. It gets carried along, frozen into the wind. This is called the interplanetary magnetic field, or IMF. As the sun rotates once every 27 days or so, the magnetic field lines get twisted into a spiral pattern, like water from a rotating sprinkler. Scientists call this the Parker spiral, named after Eugene Parker, who predicted it. Near Earth, the magnetic field lines don't point directly away from the sun. They're tilted at about 45 degrees, swept back by the sun's rotation. Farther out near Jupiter or Saturn, the spiral is tighter, the angle sharper, and this field matters. When the solar wind reaches Earth, it doesn't just carry particles, it carries magnetism. And when that magnetism interacts with Earth's magnetosphere, things happen. If the IMF is oriented southward, it can reconnect with Earth's magnetic field, opening a pathway for solar wind particles to pour into the magnetosphere. This is what triggers geomagnetic storms. This is what makes auroras. The solar wind isn't just a stream of particles. It's a conduit, a connection between the sun and the earth written in magnetic field lines. Earth is protected, not by distance, but by its magnetic field. The magnetosphere acts like a shield, deflecting most of the solar wind around the planet. On the side facing the sun, the magnetosphere is compressed, pushed back to about 60,000 kilometers above the surface. On the night side, it stretches into a long tail extending past the moon's orbit. Inside this bubble, we're safe. The solar wind flows around us, parting like water around a rock. But not all planets are so lucky. Mars once had a magnetic field. Billions of years ago, its core was molten churning, generating a dynamo much like Earth's. And for a time, Mars was protected. But Mars is smaller than Earth. Its core cooled faster. The dynamo shut down, and without a magnetic field, the solar wind struck the atmosphere directly. Over hundreds of millions of years, the solar wind stripped away most of Mars's atmosphere. What once might have been thick enough to support liquid water on the surface is now thin, cold, barely 1% the density of Earth's. Scientists suggest that this is why Mars is a desert today. Not because it was always cold, but because the sun's breath eroded it, slowly, grain by grain, until almost nothing was left. NASA's MAVEN spacecraft, which has been orbiting Mars since 2014, measures how much atmosphere the planet is still losing. Even now, Mars loses about 100 grams per second to the solar wind. A slow bleed, unstoppable. Earth could have suffered the same fate. But our magnetic field held, and so did we. Venus has no magnetic field either, but Venus has kept its atmosphere. In fact, Venus's atmosphere is thicker than Earth's 90 times denser at the surface. How? The answer is gravity. Venus is almost the same size as Earth. Its gravity is strong enough to hold on to heavy molecules like carbon dioxide, even without a magnetic shield. And its atmosphere is so thick that it creates its own barrier, slowing the solar wind's erosion. But the solar wind still affects Venus. When particles strike the upper atmosphere, they strip away lighter elements, hydrogen, helium, and carry them into space. Over billions of years, Venus has lost most of its water this way. Some scientists believe Venus once had oceans, but the solar wind combined with a runaway greenhouse effect boiled them away. And now Venus is a furnace, dry, lifeless, hotter than Mercury despite being farther from the sun. The solar wind shapes worlds, not just their weather, their climates, their futures. In 2018, NASA launched the Parker Solar Probe, the fastest human-made object ever built. Its mission to fly through the corona, to sample the solar wind at its source to understand how it's born. The probe doesn't orbit at a safe distance. It dives, again and again. Skimming just 6.2 million kilometers above the sun's surface, close enough to feel the heat, close enough to measure the plasma directly. At that distance, the probe travels at over 700,000 kilometers per hour, fast enough to cross the distance from New York to Tokyo in under a minute. And it needs to be fast. The closer it gets, the stronger the sun's gravity pulls. The probe has to move quickly, or it'll fall in. The heat is intense. The side facing the sun reaches 400 degrees Celsius. But behind a carbon composite shield, just 11 centimeters thick, the instruments stay cool around room temperature, a fragile machine threading the gap between fire and void. And it's sending back data. Measurements of the solar wind's speed, temperature, density, magnetic field. Clues about how the corona heats up. Why the wind accelerates. What drives the fast and slow streams. We've touched the sun. Not with hands, but with machines. And slowly we're learning its secrets. The solar wind doesn't end at the planets. It keeps going, past Mars, past Jupiter, past Saturn, Uranus, Neptune, past Pluto, out into the Kuiper Belt, where comets sleep in the cold. Eventually it reaches a boundary a place where the solar wind slows down, compressed by the pressure of interstellar space, the space between stars, filled with gas and dust and cosmic rays from distant supernovae. Scientists call this boundary the heliopause. It's where the sun's influence ends, where the solar wind finally stops. In 2012, Voyager 1 crossed the heliopause. It had been traveling for 35 years, launched in 1977, and it finally left the sun's domain. The solar wind vanished. Replaced by the interstellar medium, a different kind of plasma, colder, thinner, older. Voyager is now in interstellar space, the first human-made object to leave the solar system. And yet, even there, it's not entirely free. The sun's gravity still holds it. It will for thousands of years. But the breath has stopped. The wind no longer reaches. Voyager sails alone in a silence we can barely imagine. Have you ever thought about how far the sun's influence extends? Not its light travels forever, fading but never stopping, but its wind, its plasma, its breath. The heliosphere, the bubble carved out by the solar wind, is enormous, about 18 billion kilometers across. It takes light 16 hours to cross it. Voyager 1 took 35 years, and inside that bubble, everything is touched by the sun. Every planet, every moon, every asteroid, every speck of dust. All of it bathed in the solar wind, shaped by its magnetic field, connected by invisible threads of plasma. We are not isolated. We orbit inside the sun's exhalation. We live in its breath. The solar wind is not dangerous, not directly. At Earth's distance, it's so dilute that you could pass through it and feel nothing. The particles are traveling fast, but there aren't many of them. The density is about 5 particles per cubic centimeter, far thinner than the best vacuum we can create in a lab. But those particles carry energy. And when billions of them strike a magnetosphere, or an atmosphere, or a spacecraft, they add up. Astronauts on the moon during the Apollo missions were exposed to the solar wind directly. Not for long, the missions lasted only days, but long enough to measure. Their spacesuits collected solar wind particles. Their dosimeters recorded the radiation. For short visits, it's tolerable, but for long-term habitation lunar bases, Mars colonies, the solar wind is a hazard, not immediately lethal, but cumulative. Over months, over years, the radiation dose builds. We'll need shielding, underground habitats, materials that block particles, warning systems that alert settlers when a solar storm is coming so they can take shelter. The solar wind doesn't care if we're ready. It just flows, endlessly, predictably, and we're learning to live with it. The sun gives light, but it also gives wind, and that wind is part of what makes the sun a star. All stars have winds. Some are stronger than the sun's. Red giants blow powerful winds that shed their outer layers, creating glowing nebulae. Massive hot stars, O-type and B-type, lose so much mass through their winds that they can shed dozens of Earth masses in just a few million years. The sun's wind is gentle by comparison, but it's there, and it's been there for 4.6 billion years. A continuous flow shaping the solar system, sculpting comet tails, pushing against the interstellar medium, carving out a space where planets can orbit in relative calm. The solar wind is the reason we see comet tails. As a comet approaches the sun, the ice on its surface heats up, and sublimates, turns directly from solid to gas. That gas, along with dust, streams away from the comet, and the solar wind pushes it, shaping it into a tail that always points away from the sun. Not because of light pressure, though, that plays a role, but because of the wind, the sun's breath sculpting beauty from ice and dust. The sun breathes out. It has no choice. The corona is too hot to stay still, and so the plasma flows endlessly into the dark. We measure it. We study it. We send spacecraft to touch it, but we can't stop it. We can only understand it. And in understanding, we learn how to protect ourselves, how to build shields, how to predict storms, how to live in the shadow of a star. The solar wind is not a threat, it's a fact, a feature of the universe, a consequence of heat and gravity and the laws of physics. And it's beautiful, in its own way. A river that flows forever, without banks, without end, carrying the sun's essence outward into the infinite. But understanding the wind required more than theory. It required observation, ingenuity, centuries of watching, of asking questions that seemed impossible to answer. For most of human existence, the sun was a god. Ra, Helios, Surya, Amaterasu, Inti. Every culture had a name for it, a story, a temple where offerings were made. The sun gave life. It brought the day. It marked the seasons. And in return, humans worshipped. But somewhere along the way, we stopped praying and started asking questions. What is it made of? How far away is it? Why does it shine? How long will it last? And slowly over centuries, we learned, not through revelation, but through observation, through mathematics, through ingenuity and patience and the stubborn refusal to accept mystery as an answer. The story of how we came to understand the sun is not the story of one discovery. It's the story of thousands, small steps, broken instruments, failed theories, and occasionally a breakthrough so profound it changed everything. This is how we learn to see. The ancient Greeks knew the sun was far away. Aristarchus of Samos, around 270 BCE, tried to measure its distance using geometry. He observed the angle between the sun and the moon during a half-moon phase, and calculated that the sun must be about 19 times farther from Earth than the moon. He was wrong. The sun is actually about 400 times farther. But his method was sound. His tools were just too crude. The angle he needed to measure was so small that even a tiny error threw off the result. Still he tried, and that matters. He was the first person we know of who attempted to measure the cosmos using reason instead of myth. Later in the 17th century, astronomers refined the measurement using the transit of Venus, the rare event when Venus passes directly between Earth and the Sun, appearing as a small black dot crossing the solar disk. By observing the transit from different locations on Earth and comparing the timing, astronomers could use parallax, the apparent shift in position due to a change in viewing angle, to calculate the distance. In 1761 and 1769, expeditions were sent around the world to observe the transit. Scientists traveled to Siberia, to the South Pacific, to remote islands, risking their lives to gather data. And from those observations, they calculated that the sun was about 93 million miles away. Scientists now call this distance 1 astronomical unit, or AU. And it's still the baseline we use to measure distances in the solar system. The sun is not close, but it's knowable. For centuries, humans couldn't look directly at the sun without damaging their eyes. We could only glance at it during sunrise or sunset, when the atmosphere filtered its light, or during a solar eclipse when the moon blocked the disk and revealed the corona. Eclipses were terrifying events. Ancient Chinese astronomers believed a dragon was eating the sun. Norse legends told of wolves chasing the sun across the sky. In many cultures, people would bang drums, shout "pray anything" to scare away whatever was devouring the light. But by the 1800s, astronomers understood what eclipses were, and they realized something profound in eclipse was an opportunity, a chance to study the sun's outer layers, normally hidden by the photosphere's glare. During the total solar eclipse of 1868, two astronomers, Pierre Janssen in India and Norman Lockyer in England, independently observed the sun's spectrum using a device called a spectroscope. They noticed a strange yellow line in the spectrum, one that didn't match any known element on Earth. Lockyer proposed that it belonged to a new element. He called it helium, after Helios, the Greek sun god. At the time, helium had never been found on Earth. It was discovered on the sun first. It wasn't until 1895, nearly 30 years later, that helium was isolated in a laboratory extracted from uranium ore. We found an element in the sun before we found it on our own planet. The sun taught us chemistry. Spectroscopy changed everything. By splitting sunlight into its component wavelengths, essentially creating a rainbow, scientists could see dark lines where certain wavelengths were missing. These lines, called absorption lines, were caused by elements in the sun's atmosphere absorbing specific colors of light. Each element has a unique pattern of lines. Hydrogen has its own signature. So does helium, calcium, iron, magnesium. By studying the spectrum, scientists could determine what the sun was made of without ever touching it. In the early 1900s, astronomer Cecilia Payne analyzed the sun's spectrum and concluded that the sun was made primarily of hydrogen and helium. At the time, most scientists believed the sun had roughly the same composition as Earth, mostly iron, silicon, oxygen. Payne's conclusion was dismissed. Some called it impossible, but she was right. Later measurements confirmed it. The sun is about 73% hydrogen, 25% helium, and only 2% everything else. Payne's work was one of the most important discoveries in astrophysics, and for years, she didn't get the credit she deserved. Science is not always fair, but eventually, the truth wins. In the 20th century, we began launching instruments into space, not because we wanted to, but because we had to. Earth's atmosphere blocks most wavelengths of light, ultraviolet X-rays, gamma rays. From the ground, we could only see visible light and some infrared and radio waves. To see the full sun, we needed to rise above the air. In 1960, NASA launched the first successful solar observatory satellite, OSO-1. It carried instruments to measure X-rays and ultraviolet light from the sun. For the first time, we saw the corona, not just during eclipses, but constantly in wavelengths invisible to human eyes. The images were strange. The sun didn't look smooth. It looked mottled, textured, dynamic. There were bright regions above sunspots, active regions glowing intensely in X-rays. There were dark regions near the poles, coronal holes, where the magnetic field was open and the plasma escaped. The sun was not a perfect sphere. It was alive with structure, with motion, with complexity we'd never imagined. And the more we looked, the more we found. In 1973, NASA launched Skylab, America's first space station. One of its primary missions was to study the sun. It carried a suite of telescopes designed to observe the sun in ultraviolet and X-ray wavelengths, capturing images and spectra for months. Skylab discovered coronal mass ejections, those massive eruptions of plasma we talked about earlier. Before Skylab, we didn't know CMEs existed. We knew about flares, but we didn't realize the sun could hurl billion-ton clouds of plasma into space. Skylab watched the sun erupt, and it recorded the data. Film canisters were brought back to Earth by astronauts developed analyzed. And from those images, scientists began to understand how dangerous the sun could be. We hadn't just learned to see the sun, we'd learned to see its temper. In 1995, the Solar and Heliospheric Observatory, SOHO, was launched. It orbits at a point called L1, about 1.5 million kilometers from Earth, where it has an uninterrupted view of the sun. For nearly 30 years, SOHO has been watching. It has observed over 5,000 comets, small icy bodies that plunge toward the sun and either swing back out or evaporate entirely. Most of these were never seen from Earth, too faint, too close to the sun's glare. But SOHO's instruments designed to block the photosphere's light could see them. SOHO has also tracked the solar cycle in exquisite detail, every sunspot, every flare, every CME. The data it has gathered is unmatched, and it's still operating decades beyond its original design life. Scientists sometimes joke that SOHO refuses to die. It was built to last 3 years. It's been observing for 29. The sun is patient, and so are the machines we send to watch it. In 2010, NASA launched the Solar Dynamics Observatory, SDO. It's faster, sharper, more advanced than SOHO. It captures images of the sun every 0.75 seconds in 10 different wavelengths at a resolution high enough to see features the size of Texas. If you've ever seen a video of the sun plasma swirling flares, erupting prominences arcing, it probably came from SDO. The spacecraft has produced petabytes of data, millions of images, a continuous high-definition movie of the sun streaming back to Earth in near real time. And it's not just for scientists. The images are public. Anyone can see them. NASA releases them online, updated daily. You can watch the sun right now as it's happening. We've made the sun visible to everyone, not as a god, not as a symbol, but as it is, a ball of plasma, a star, a thing we can study, understand, predict. The Parker Solar Probe, launched in 2018, is our most ambitious mission yet. It doesn't just observe the sun from a distance. It dives into the corona, closer than any spacecraft has ever gone. At its closest approach, Parker is only 6.2 million kilometers from the sun's surface. That might sound far, but it's not. Mercury orbits at about 58 million kilometers. Parker gets 10 times closer. The heat is immense. The side of the spacecraft facing the sun reaches 400 degrees Celsius. But behind its heat shield, a slab of carbon composite just 11 centimeters thick, the instruments stay cool around 30 degrees Celsius. Room temperature, in the shadow of fire. Parker measures the solar wind directly. It samples the plasma. It tracks the magnetic fields. It watches how the corona heats up, how the wind accelerates, how energy flows from the sun's surface into space. Research shows that Parker has already discovered something unexpected: switchbacks. These are sharp kinks in the magnetic field, where the field lines suddenly reverse direction, forming S-shaped curves. Scientists aren't sure what causes them. Magnetic reconnection maybe, turbulence in the corona, something we didn't predict. The sun is still surprising us. Even now, even with all our instruments, all our models, all our centuries of watching. Have you ever thought about how strange it is that we can study the sun at all? That we can measure its temperature, its composition, its magnetic field without ever touching it? We do it with light, with spectra, with the Doppler effect, which tells us how fast things are moving, by measuring shifts in wavelength, with helioseismology, which lets us hear the sun's interior by watching its surface vibrate. We have turned light into a tool, a probe, a way to reach across 93 million miles and read the sun's secrets. And the sun, for its part, doesn't hide. It broadcasts. It shines. It sends neutrinos, solar wind flares, CMEs. It gives us data constantly, whether we're ready for it or not. We just had to learn how to listen. In ancient Egypt, the sun god Ra sailed across the sky, in a boat fighting the serpent of chaos every night. In ancient Greece, Helios drove a chariot pulled by fire-breathing horses. In Norse mythology, the sun was chased by a wolf, and one day the wolf would catch it. These were stories, beautiful, poetic, meaningful. But they weren't true. The truth is stranger. The sun is a sphere of plasma held together by gravity, powered by fusion, surrounded by a magnetic field, exhaling a wind that fills the solar system. It's 4.6 billion years old. It will burn for 5 billion more. And it's one of hundreds of billions of stars in the galaxy. We are not special. The sun is not unique, but it's ours. And we've learned to understand it. Not perfectly, not completely, but enough to predict its storms, enough to measure its heartbeat, enough to send a spacecraft into its atmosphere and bring back data. We've gone from worshiping the sun to studying it. And in doing so, we've discovered something profound. The sun is not a god, but it's no less magnificent. The journey from myth to mission took millennia. It required telescopes and satellites, mathematics and spectroscopy, patience and risk. It required people who looked up and refused to accept mystery as the final answer. And it's not over. We're still learning. Still launching missions, still asking questions. How does the corona heat up? What triggers flares? Can we predict solar storms more accurately? How will the sun's brightness change as it ages? What will happen when it finally dies? We don't have all the answers, but we're getting closer. And the sun, indifferent to our efforts, continues to burn, continues to shine, continues to give without asking anything in return. But all things end. All stars fade, and the sun, patient and ancient as it is no exception. The sun will not burn forever. One day far from now, impossibly far but still inevitable, the hydrogen in its core will run out. The fusion that has sustained it for billions of years will falter. The light will dim, and the sun, patient and steady for so long, will begin to change. Not suddenly, not violently, but gradually over millions of years it will swell, it will brighten, it will consume the worlds that orbit closest to it. And then quietly, it will fade. This is not a tragedy. It's just physics. It's the life cycle of a star. And the sun, like all stars, is mortal. But not yet. Not for a long, long time. 5 billion years from now, the core will have converted most of its hydrogen into helium. The fusion rate will slow, and without the outward pressure from fusion gravity, will begin to win. The core will contract, and as it does, it will heat up. The outer layers of the sun, feeling the increased heat from below, will expand. The sun will grow larger, brighter, hotter at the surface, even as the core compresses. Scientists call this phase the red giant stage. The sun will swell to perhaps 100 times its current size, large enough to engulf Mercury, large enough possibly to reach Venus, maybe even Earth. If you could stand on Earth, then of course you couldn't. You'd see the sun filling half the sky. A vast, bloated sphere glowing deep red, its surface cooler than now, but so much closer that the heat would be unbearable. The oceans would have boiled away billions of years earlier, the atmosphere stripped by the solar wind, the surface molten glowing faintly with its own heat. Earth would be a cinder orbiting inside the dying star's outer envelope. But by then humanity will be long gone, either extinct or scattered among the stars, or evolved into something we can't imagine. The Earth as we know it will be a memory, a fossil, a place that once held life briefly in the long history of the cosmos. The sun will not explode. It's not massive enough for that. Supernovae require stars at least 8 times the sun's mass. The sun will die gently by stellar standards. After the red giant phase, the core will continue to contract. Eventually, it will become hot enough around 100 million degrees Celsius to fuse helium into carbon and oxygen. This will give the sun a second life, a brief resurgence. The outer layers will contract slightly. The sun will shrink, cool, stabilize. But this phase won't last long. Maybe 100 million years, the helium will run out. And the core, now made of carbon and oxygen, will not be hot enough to fuse those elements. The sun's mass isn't sufficient. Fusion will stop. And without fusion, there's no outward pressure. The core will collapse one final time, compressing into a sphere about the size of Earth. The density will be staggering. A teaspoon of core material would weigh a ton. This is called a white dwarf. Not a star anymore, not burning, just a hot, dense ember radiating away its remaining heat over trillions of years. The outer layers no longer supported will drift away, gently, beautifully, forming a glowing shell of gas, a planetary nebula. Not because it has anything to do with planets, but because early astronomers looking through primitive telescopes thought these nebulae looked round like planets. The nebula will expand, fade, and eventually dissipate. And all that will remain is the white dwarf, silent, cooling, slowly dimming into a black dwarf, a cold, dead cinder, invisible against the dark. The sun will have become a ghost. But that's billions of years away. Right now, the sun is in its prime, middle-aged, stable, predictable, fusing hydrogen at a steady rate, shining with a light that has barely changed in the entire span of human existence. We often think of the sun as eternal, as unchanging. But it's not. It's aging, slowly. Every second, it converts a little more hydrogen into helium. Every second, the core becomes slightly denser, slightly hotter. Every second, the sun grows a tiny bit brighter. Research shows that the sun is about 30% brighter now than it was when it first ignited 4.6 billion years ago. If Earth had formed with the same atmosphere it has today, the early Earth would have been frozen solid, but it wasn't. Life emerged. Oceans flowed. Something else must have kept the planet warm, likely a thicker atmosphere rich in greenhouse gases. As the sun brightened, the atmosphere thinned. And by sheer chance, the rate of brightening and the rate of atmospheric change balanced each other. Earth stayed habitable for billions of years. We'd live in a Goldilocks moment, not just in terms of distance from the sun, but in terms of time. The sun is bright enough to warm us, but not so bright that it scorches us. And it will stay this way for perhaps another billion years. After that, the balance will tip. The sun will grow too bright. Earth will heat up. The oceans will evaporate. And the window for life, our window, will close. But a billion years is a long time. Long enough for evolution to reshape life 1,000 times over. Long enough for civilizations to rise and fall, to spread to other worlds, to perhaps outlive the sun itself. We are not bound to this planet, not anymore. We've already sent machines to other worlds. We've walked on the moon. We've studied Mars. We're planning missions to Europa, to Titan, to the icy moons where liquid water hides beneath frozen shells. One day we might leave. Not because we want to, but because we have to. Because the sun, our ancient protector, will become our enemy. But not yet. Have you ever thought about what it means to live in the light of a dying star? Not dying now, not soon, but dying eventually. Every photon that warms your skin, every ray that feeds the plants, every sunrise you've ever witnessed, they're all part of a process that will someday end. The sun is not infinite. It had a beginning, it will have an end. And we, tiny and brief as we are, exist in the middle, in the calm, in the time when the sun is kind. This is not depressing, it's humbling. It's a reminder that nothing lasts forever. Not stars, not planets, not species. Everything changes, everything fades. But that doesn't make the light less beautiful. In 1977, NASA launched Voyager 1 and Voyager 2. They carried Golden Record's actual phonograph records etched with sounds and images from Earth. Music, greetings in dozens of languages, pictures of humans, of cities of nature. A message sent into the cosmos in case anyone is out there listening. The records also included a diagram, a map, showing the location of the sun relative to 14 pulsars rapidly spinning neutron stars that emit regular pulses of radiation. Using the pulsars as reference points, anyone who finds the record could in theory trace the path back to our star, back to the sun. It's strange, isn't it? We spent millennia trying to understand the sun, and now we're telling the universe where to find it. The Voyagers are in interstellar space now, beyond the heliopause, beyond the sun's wind, drifting in silence, carrying their golden messages, traveling at 60,000 kilometers per hour. In 40,000 years, Voyager 1 will pass within 6 light years of another star, Gliese 445. By then, the sun will still be shining, unchanged, patient, but the Voyagers won't return. They'll drift forever, or until they're destroyed by dust or captured by some other star's gravity. They're the farthest human-made objects from the sun, and they're still, in a sense, the sun's children. We are all the sun's children, made from its light, fed by its warmth, held by its gravity. And one day, we'll have to say goodbye. But tonight the sun is still there, on the other side of the world, shining on someone else's morning. In 8 minutes, its light will reach us again. It always does, every day, without fail. We take it for granted. The sunrise, the warmth, the blue sky. But none of it is guaranteed. The sun could flare, could storm, could in theory hiccup in ways we don't expect. But it doesn't. It just shines, steady, reliable, indifferent to whether we notice. And maybe that's the most profound thing about the sun. It doesn't care. It doesn't love us. It doesn't protect us intentionally. It's just a star doing what stars do, fusing hydrogen, radiating energy, following the laws of physics. And yet, because of it, we exist. Because of it, life happened. Because of it, there's warmth and light and beauty and time enough to wonder why. The ancient Egyptians believed Ra sailed across the sky each day and journeyed through the underworld each night, battling darkness. The Greeks believed Helios drove a chariot of fire. The Aztecs believed the sun needed blood to keep burning. We know better now. The sun doesn't need us. It doesn't need anything. It burns because it must, because gravity and heat and pressure leave it no choice. But maybe there's something poetic in that. The sun gives without asking. It shines for everyone, for the just and the unjust, for the oceans and the deserts, for the living and the dead. It doesn't choose, it just is. And in being, it gives everything. So rest, let the thought settle, let the immensity of it drift gently through your mind. You are standing on a small world orbiting a medium-sized star in an unremarkable corner of a galaxy that contains hundreds of billions of others. The sun is one star among billions. And yet it's the only one that matters to us. It's the one that made us, the one that feeds us, the one that will someday, long after we're gone, grow and swell and fade. But tonight, it's just the sun, familiar, constant, a point of light that will return in the morning as it always has. And maybe that's enough. We've walked through fire tonight, through the birth of a star, through the layers where light is born, through the storms and the wind, through the music of plasma, through the history of watching and wondering. We've seen the sun not as the ancients saw it, but as it is. A ball of hydrogen turning into helium, releasing light one photon at a time for 4.6 billion years. We've touched its surface with machines. We've measured its heartbeat. We've mapped its interior. We've learned to predict its tantrums. And still it remains vast. Still it surprises us. Still it holds secrets we haven't unlocked. The sun is knowable. But it's not finished teaching us. Thank you for drifting here with me, for letting curiosity lead, for resting in the strange, quiet beauty of a star that burns 93 million miles away and yet touches everything. The sun will rise again. It always does. And when it does, maybe you'll see it differently, not just as light, but as fusion, as plasma, as wind and magnetism and vibration, as a thing that has been and will be long after we're gone. Sleep well, dream gently, and when the light finds you again, remember, you are made of stardust. You are warmed by a dying star. And for now, in this brief bright moment, you are here. Good night. And if you found comfort in this quiet journey through fire and time, stay with us. There are more stories waiting, more wonders to unfold softly beneath the night. Until then, rest.